All right, everybody, let's talk about geologic mapping and cross sections. These are powerful informational tools for the geologist, and they can be a bit challenging to learn how to do and learn how to read. You might remember this map of Grand Canyon that I showed you last time when I was introducing the stratigraphic principles. Let's have a look at what's going on this map. You'll see that there's a variety of colors. Each of these colors are represented in the legend. The legend is organized by geologic time. It follows the principle of superposition. That is, the oldest units are on the bottom and the youngest units are on the top. Everything in between is placed in order, and each color is referring to a specific rock type. In a full legend, the rock types would also have a description beside them that describes their texture, any variations, and that kind of thing. In addition to the colors, each of the rock units has a symbol, letters, or letters that you might not recognize as being regularly used letters. And these symbols are a combination of the rock unit and its geologic time. So for example, the Carboniferous is of geologic time, and so the red wall limestone, which is marked in pink, is indicated with a C and an R. C for Carboniferous and R for red wall. Just below it, older, in the Cambrian, is the Mauve limestone, and that symbol is a C with a line through it and a little M. The C with a line through it is the symbol we use for Cambrian, because we can't have more than one C, that would be confusing. And the little M is for Mauve. So throughout the entire legend, we've got symbols, rock type names or description, and a color for each of those rock types. And again, very importantly, they are organized with the oldest units on the bottom following the principle of superposition. If we look at that same location in a satellite view, you can see the topography quite clearly. The topography is the shape of the landscape. If I flip back to the earlier image, all of these dendritic patterns that you can see outlined in all of the different colors of the rock types are there because of the topography, because of the rivers that have cut through and eroded away the landscape rocks. So in this satellite image, you can make out those same shapes, which are all the little valleys leading into the main Colorado River below. If we look at it without a satellite image, but instead just topography, this specific dendritic pattern is much clearer. Each of the rock units, as I mentioned in the last lecture, are horizontal. And you can't see them obviously in this topographic map, but because of the way the shape of the valley is set up, you can see each layer of the topography exposed in that bird's eye view. So if we have a look at the very bottom where you see part of the geologic map exposed, these stripes of colors are following every topographic contour in the map. Now if we zoom in a lot more to the same map, we can see some more information beyond colors and symbols that are the letters. And these symbols are other geologic structural symbols, and we are very interested in them for our beginning geologic mapping. Strike and dip, I will explain later. These are our orientation tools. We follow a convention as geologists in how we measure geologic structures. So we all use what we call the right hand rule, where we use our right hand, that's the rule, to measure strike and dip. And this is for consistency primarily. There are other symbols on here following lines. These are sometimes labeled with the word fault. So you can see fault showing up a couple of times here. So on this map, we've got strike slip faults indicated. So that's probably what these are. And then we also have these symbols with arrows, and these are indicating folds. Let's see if I can, I don't think I can see a fold in this super cropped zoom in. Now you might remember that I mentioned the tool Visible Geology, a free web app, and I encourage you again to go online, set up some horizontal stratigraphy, and erode it in different shapes so that you can see how these geologic layers show up when you add topography to the Earth's surface. So it's really takes quite a bit of practice to be able to clearly see 3D geologic visualizations. You might also remember this very high quality drawing that I provided for an exercise last time. So now I'm going to task you with, how would this look in map view? Let's just erase most of it and have a look at these lower, slightly folded layers. How would this look in map view? Well, maybe before we get there, let's look back at this whole thing. What are we looking at here? This is a side view. This is like a slice through the Earth. I have a little sheep on the top representing the Earth's surface, and we're like looking underground beneath the sheep's feet to see all the layers of earth and rock beneath it. So when I ask you how would we see this in map view, what we're looking at is the vertical plane. So if we imagine removing a 3D cube of earth material, what would the top surface look like if this is one of the sides? This side view is what we call a cross-section view in geology. So now let's erase most of that and just look at that curved, folded lower portion. I'll maybe clean that up a little bit and blow it up a little bit, and we can see now in our side view, if we want to represent this on the top surface, we need to do a fair bit of projection. The first thing is figure out what it is we're seeing. Well, here in our side view, we can see that it's fully curved. But imagine we didn't have all that information. We just had a small portion of it. We would take measurements of each of these layers and mark them, which you can see as the little blue tick marks all the way along. And we would infer from the shapes of those tick marks that these must actually have once been connected into a large overturned or a large arch-shaped fold. So now that we have this inferred information from our measurements, we want to put it together into what would the surface look like. Well, in this case, if it's a simple fold, we can imagine that all of the components of these rock units were sliced through like we took a layer cake and we bent it and then we sliced the top off. And that's really what the map view is. Now, we never do this in geology. We never have a side view readily accessible. We only ever have the top view. So what we actually want to be able to do is take our surface map view and project that into 3 dimensions and visualize the side. So if we started with these units, you would immediately notice that there's a pattern. We have white, blue, purple, orange, purple, blue, white. There's a distinct repeating pattern. And that distinct repeating pattern is symmetrical. Left side matches right side. So how would we get that geologically? Well, we can either bend it this way or we could bend it this way. And this is where the important measurements of strike and dip come in. So stick with me, we'll get there. So let's take a look at this map view for a moment. Here we have several pieces of information that are provided. The dotted lines are topographic contours. And you know from our map of the Grand Canyon that topographic shapes can impact how the colors of rock units representing those shapes can appear in the map view. We have also on here 5 distinct rock units, speckled, dark gray, yellow, white, and medium gray. We have a line marked A to A prime, A apostrophe we refer to as A prime. We have a north arrow, and we've got all of these little strike and dip symbols. Strike and dip symbols are this sort of funny T, and they have an angle in degrees marked on them. This angle marked in numbers is the dip angle of our strike and dip. The dip angle is the number of degrees down from horizontal. If you just look at my hand, down from horizontal, that layer is measured to be dipping into the ground. So if we imagine the Earth's surface is horizontal, and then we have that rock layer is dipping down, going underground beneath our feet, that angle is the dip measurement. So if we're looking at this map view and we want to imagine what it looks like underground, that dip measurement is super key. But line A to A prime, we like to mark on our map surface where we are trying to visualize underground. This is our cross-section line. Below the map, I've drawn for you a cross-section box, which is where we're going to fill in with the information we have on the map view and infer what it looks like underground. So the 0 is the 0 elevation line, and all of these other numbers, 100 meters, 200 meters, 300 meters, 400 meters, is elevations above 0 sea level. So all of these contours for the topography, I will mark with a topographic profile. So you can see here I have these elevation numbers. So 100 is 100 meters, etc. So that's our topography information. So to show you how that gets plotted on here, if we take our cross-section line, A to A prime, we have to see where do those contour lines intersect with our cross-section line. Where they intersect is where we know it is that elevation. So I've drawn in blue here where the 100 intersects, where the 150 intersects, etc., and plotted those elevations on my cross-section line below. So my lowest elevation in this map area is 100 meters. It's on this topographic line that I want to relate my underground information from these dip angles. So let's look at that next. So I have a few pieces of information, not very many for dip angle, and I'm going to have to use my best approximation to assume it's pretty similar across that cross-section line. Since my cross-section line doesn't intersect any of those measurements, and these measurements can't be simply projected down because they're at a specific rock where they were measured, we just have to take our best guess. But you'll see that these numbers are all pretty similar to each other, so we have a good starting point. So remember, the dip is the degrees down from horizontal. So in this diagram, you can see if I measured the specific rock surface and I measured the degrees it's dipping down into ground. So 20 degrees down for this diagram example. And on our map, you can see they're 14 degrees. The other thing that's really important in the strike and dip symbol is the direction that dip line is going. So on our map, you can see the little dip angle line is pointing to the right. And on this diagram, it's pointing more or less to the left. And this is the dip direction. So if I translate this information down to my cross-section line, I need to make sure that my dip at 14 degrees using a protractor is also pointing to the right. Otherwise, it would be pointing in the incorrect direction. So within our real world scenario, let me show you what this might look like if we were actually measuring it. We would take a compass and lay it on its side to measure the angle of dip. So in the compass on the inside, there is a clinometer, which is a slope angle reader, and you can read that angle of dip down directly off of the compass. Now the other thing that's going on in this image is measuring strike. So here we have the compass that is oriented perpendicular to the dip angle. So if we go back to this diagram here and back to our map, we can see that the strike and dip symbol, which looks kind of like a capital T, the capital T makes right angles. The strike line is the orientation of the rock unit in a 360-degree map orientation. So we're looking at a horizontal plane, a bird's eye view plane. Which orientation does that rock have within 360 degrees of a plane on the horizontal surface of our small area of Earth, which we can approximate as horizontal for the unit we're looking at? So if we look at this cartoon diagram in the background, this long line is the strike direction. The strike direction is measured using our right hand rule. If you take your right hand and you set it down on the rock surface, you've got your fingers that are going to go down the dip of the rock and your thumb that will point in the strike direction. So if you orient your hand so that you have a right angle between your thumb and your fingers on your right hand, you can do the right hand rule. Your thumb is going to point along strike, and your fingers are going to flow down dip, down underground. So if you were to put your hand virtually onto the cartoon diagram, you would see that the strike direction on this particular cartoon is pointing out of the screen to the right and down. And on this rock surface, you could put your hand on, you can see the direction that they're measuring that slope. You put your hand on it with your fingers pointing down the dip direction, and your thumb is going to point along this surface of the rock going into the screen and out of the screen pretty well the same way as the cartoon. So that angle is the strike angle. So when we're out in the field measuring strike and dip, we measure with a compass, and we use our right hand rule, and we gather a list of measurements. The convention is to set up your field notebook where you number your field stations, and then you record one column with your strike measurements and one column with your dip measurements, and then another column with your rock information for that location. So now let's get back to plotting this onto a cross section. So we have our dip angles, which happen to all be the same. And we know that based on this symbol, that dip angle is pointing to the right every single time. So now we want to project them down onto our cross-section line to the best of our ability. So here's how we're going to do this. These measurements, they're from some random rock somewhere within this rock unit. So if we were to just map straight down, we know it's going to be a bit of an approximation. So what I want you to see here is, as I've projected them directly down to that cross-section line, some of them land below the Earth's surface, some of them land above the Earth's surface. I could actually have plotted them all on the Earth's surface. But you'll notice I've done something else. What I've done is I've dropped down in red the contacts between each of the rock types. So the contact line all cross, each of the contact lines all cross our cross-section line. And what we know about this piece of information is this is the intersection between speckled rock and gray rock. Speckled rock on this side, gray rock on this side. And then this is the intersection between the gray rock and the yellow rock. So this we actually call a geologic contact. So gray rock on this side, yellow rock on this side, and so on. So these points we know are where the two rock types meet. Now we have a more reasonable place to use our dip information. So this measurement says the yellow rock is dipping at 14 degrees. In fact, all of them say they're dipping at 14 degrees. So what we want to do is take all of these dip measurements and measure 14 degrees down from horizontal at each of the contacts between the rock types. Because what that tells us is that it's likely each of these rock layers are all dipping parallel and 14 degrees. So just to remind you again, on this diagram, you can see that dip direction. You can also see these rock layers, that they are all parallel in this photograph. So let's plot that. So now that I've drawn that in, all of these lines, 14 degrees, all of these rock units, dipping parallel to each other, they were probably all laid down horizontally, following the law of original horizontality, and then tilted together to result in this sequence of rocks being all parallel dipping, and then eroded to give the landscape shape, and in the map view explain these strange wiggles in the different colors of rock units. If we look at satellite images in Google Earth, we can see parallels to this. So this is a shot over Iran, and we can see all of these different colors of sandstones and limestones that are exposed in stripes because these units are horizontal and then eroded down. If we look at it in side view, we can see those angles of those rock units very clearly and how each of those horizontal units are exposed and look instead like they're crinkled and folded like an accordion. Similarly, in Utah, we have the same kind of situation, more horizontally layered sedimentary rocks. And here we can see that they're all eroded with these dendritic patterns of desert ephemeral streams. And again, if we go inside view, we can see why the patterns look like they do. Here, clearly on the top of this hump, we can see these horizontal units, but it has actually been gently folded here. So those same units by lateral continuity continue, and it's been strangely eroded down the sides. And all of these rock units would have one time been intact prior to erosion. So strange and crazy map view patterns are the result of erosion and also of geologic deformation. So to wrap up, the connection between a map and a cross-section in the simplest possible view, let's look at these two. We have this basic map. We've got contacts between all of the rock units, and it's representing this geologic cross-section. So in cross-section, it looks much more complicated than it does in map view. And that's because this map here is missing some very valuable information that would tell us about these angles of dip of these rock units. Just looking at this map view, you would have no idea that this is actually an intrusion. But if we had a measure and a strike and dip mark on this dike that has intruded through these rock units, we would see that it's dipping nearly vertically. Whereas this line right here would suggest that this is a fault that's dipping to the left, whereas this rock unit is dipping, the contact is dipping to the right, and this contact is dipping to the right. So we need the combination of rock types and units and these strike and dip measurements to orient ourselves and figure out our best guess as to what any geologic area looks like underground.